Welcome everybody to the second session of our monk show. And the first speaker will be Stefano Baiguera from Niels Bohr Institute. And he'll tell us about non-relativistic near-BPS corners of n-equal form supermills with S1 symmetry.
Okay, thanks a lot for the introduction and for this opportunity to give this gong show. And as you said, I will discuss about particular limits of n equal to 4 super mills with this particular symmetry structure. Now, the starting point is the well-known ADS-CFT duality, where we all know that the most famous application and example relates n equal to 4 super mills with type 2B string theory. In particular, one of the greatest successes that is very clear for this audience is that in the planar limit n equal to infinity, the power of integrability allows to find a description in terms of a spin chain that is able to find relations between the bulk and the boundary and obtain powerful results. But one of the problems of this approach is that gravity enters only via 1 over n perturbative corrections, and so we don't have access to non-perturbative phenomena like black holes and D-branes. In order to overcome the limitations of this approach, the proposal that I will discuss in this talk is to consider particular limits which give rise to the so-called spin matrix theories introduced by Armar, Corselli, and collaborators in many papers, where the main idea is that we put n equal to 4 super mills on R times the 3 sphere, and we zoom in towards a unitarity or a BPS bound. In this way, by performing a sphere reduction, the theory reduces only to a subsector where only some of the degrees of freedom survive the limit. And in particular, these sectors are closed in the sense that only one loop contributions of the dilatation operator enter the game. In the picture, I described what is the idea of this procedure. The black bar denotes the non-perturbative effects like black holes and D-branes. The blue bar is the planar limit, where we have the integrable spin chain entry-level string theory. And the red bar, spin matrix theory, is a particular region of the parameter space where ADS-CFT duality applies, where we are able to find an overlap between these two regimes. Now, with spin matrix theory limit, we are not considering we are restricted to a particular corner of the duality, in particular a corner where the theories that we find are non-relativistic. And various ways to see this fact come from the presence of an emergent U1 global symmetry that arises in all of these models and is interpreted as being mass conservation, a typical symmetry in non-relativistic theories. From the bulk perspective, these spin matrix theories have a very clear description in terms of non-relativistic string theories, in the sense that the target space is given by a non-Lorentzian geometry. And also one can see that one can perform further limits where also the worldsheet is non-relativistic. In this scheme, I describe what is the procedure that we follow in this talk to obtain one such spin matrix theory Hamiltonian at quantum level, starting from the classical n equal to 4 super Young-Mills action. The standard procedure that was performed previously in the literature, for example, by Bizert and other papers, is to first study the quantization of the dilatation operator and then restrict to a near-BPS limit in order to consider particular sectors of the theory. What we did instead is to, first of all, impose the near-BPS limit, which means performing the sphere reduction at classical level, finding a classical Hamiltonian, and then give a prescription to quantize the theory. In this way, the two procedures we have shown that give the same result, but following this different path, we can see that the quantization procedure is much simpler because we simply give a prescription to quantize the classical Hamiltonian, and self-energy corrections arise only from normal ordering without any need to compute loop corrections of the dilatation operator. Now, focusing in more details into the specific near-BPS limits, we consider limits of the form given by equation 1, where you can see there are the various Cartan charges on the free sphere. But one relevant fact is that one of the Cartan charges for rotations, S2, does not appear in this bound, in this inequality. And this is why we are restricting to limits with SU11 symmetry or some other spin group which contains SU11 as a subgroup. If you turn on also S2, then you will obtain SU12 symmetry groups or generalizations. The spin matrix theory limit is given by this equation 2, where you can see that there is a combination that is required to be finite, but n is not sent to infinity, is just fixed, which in fact allows to overcome the limitations of the planar limit. When you send n equal to infinity, then you can recover the planar limit. For this talk, I will focus on one sector, SU11/1, which is the simplest one where there is supersymmetry. The procedure to perform these various steps is written here. First of all, you impose a near-BPS limit at quadratic level, and this allows to isolate the propagating degrees of freedom of the theory. Then you need to integrate out additional non-dynamical modes that can give rise to effective interaction in the given limit. In particular, the gauge field plays a very important role. And finally, we derive the interacting Hamiltonian by following imposing this, computing this equation, the equation 3. I give you directly the result of the procedure, and the interacting Hamiltonian, you can see that it is very simple in the sense that everything is encoded in two quantities. Charge density, whose zero mode, the corresponding value for L equal to 0 corresponds to the SUN singlet constraint, or at classical level, which then vanishes. And at classical level, you can see that this quantity Q0 vanishes due to Gauss law. This implies that the second line in this equation identically vanishes. And the other block instead gives an interaction between scalars and fermions. This Hamiltonian has a global U1 symmetry, as I anticipated, corresponding to mass conservation. It commutes with all the generators of the algebra, as one can see by direct computation, and also is positive definite, which is very important for example, for studies at large coupling. Now, to conclude this talk, I will give you two results that I will not show. I will not have the time to show, but are found in the paper and can be shown explicitly. The quantization prescription consists, as I said, to give a prescription to quantize this classical Hamiltonian. And here we directly promote the Hamiltonian at quantum level, which allows, by computing normal ordering and giving rise to self-energy corrections, to match the quantum Hamiltonian with the previous result from the literature found following the other method. Also, there is a very nice local formulation, or semi-local more precisely, in the sense that everything can be described in terms of a 1+1 dimensional field theory, in terms of these fields, a scalar and a fermion, where, however, we sum only over positive modes, which means that the commutation relations are not delta functions, but some truncation where we sum only over positive modes. Also, the action can be written in terms of a superfield, which combines the scalars and fermions in this way. But except for these non-standard commutation relations, the action will be local and a usual quantum field theory action. Instead, some hints for future developments are the investigation of these limits for the SU12 cases, which are the most general possibilities. It's a work in progress that we are studying now. One can also study the holographic part, the bulk side, where we have some non-relativistic formulations of string theories. And in particular, the biggest group, SU12/3, has a supersymmetric black hole solution whose microscopic origin is not well known, and so it can also be interesting to study aspects of this black hole from the perspective of spin matrix theories. And with this, thank you for the attention.
Okay, thank you. Let's unmute ourselves. Thanks.
Thank you.
Renny, it's hard to hear you actually. No.
Sorry.
Evgeny, it's not you.
Okay.
Any questions?
Now, please questions. Comments.
So I can ask them.
Sorry, this construction that you were doing, can you do it in the ABJM model as well?
This I don't know, because with this particular construction, it works because you can find some particular sectors of n equal to 4 Sperling Mills where you are sure that the dilatation operator contributes only into one loop, and this allows to find these particular sectors where you can find these powerful results. I a priori, I would not say that it is so simple to apply also to a BJM.
There are, I mean, close sectors there as well. They're
yes.
at 2 loop, I suppose, but it might be interesting to look at.
Yes. Yes, because I think that here also the fact that it was at one loop was quite crucial, but maybe the computation can be more difficult, but one can still maybe obtain some particular limits for this sector of ABGM. One needs to go to higher loops, so probably there will be more complications, but it's possible that you can still identify some particular region of parameter space where doing these investigations, but I don't know a priori.
Thanks.
Yeah, well.
Sorry, cool. So I just maybe missed. What can you actually compute with this Hamiltonian? So
yes, at this point, this Hamiltonian is written in terms of various modes where you sum only over positive values. But one interesting fact is that one can find this kind of local formulation. So, for example, if one wants to go at strong coupling, this interacting Hamiltonian would be multiplied by some coupling constant. And for example, the fact that this is positive definite allows to find that if you go to couplings going to infinity, for example, you know that at leading order, you simply need to put to zero this interaction to find the solutions. So this can allow maybe to investigate properties at strong coupling in a simplest way, or also since the holographic duals are well known in terms of these non-relativistic string theories, it can also be useful to find a test of ADS-CFT duality in these non-relativistic sectors. But the idea should be also that if one learns some lectures from these particular limits, then one can try to apply some techniques also for the general relativistic case or other sectors of ADS-CFT duality.
But so what's the answer to my question? So what can you actually compute with the Hamiltonian?
Okay, in principle, since this matches with the previous computations, so you can treat this as a spin chain Hamiltonian as it was done in the planar limit. You can study the action on the states.
The point was you're not in the planar limit.
No, exactly. And so, for example, I would say that these things where you can study the strong coupling limit at leading order, even outside from the planar limit, can be interesting by itself. But if you find a quantum field theory formulation, then you can study this theory as a theory by itself and try to study its properties, correlation functions. You can try to quantize as a usual theory. You only have this constraint that the commutation relations are not Dirac delta functions, but more different. But we have a quantum field theory action where you can study.
But can you take n to be like 2 and diagonalize this?
Can I take, sorry?
N to be 2.
Yes.
Finite n. And
yes.
Diagonalize to find the spectrum at finite n. Or
I would say that
Because a quadratic
I
is
want to-
Newtonian, isn't it? So
yes, yes,
Yeah.
yes, it is. Yes, this part is quartic because it contains a tag ref,
all right.
and everything is quartic because it is a square of blocks that are quadratic in the fields.
Oh, okay. We actually run out
Yeah.
of the time. Let
Okay.